Hi there. In the following video I will show you how to perform and use Prim's algorithm for finding the minimal spanning tree of a network. To start with, a few definitions just to remind ourselves of key terms we're going to need. What's a graph? Well, all a graph is a collection of vertices or nodes and edges or arcs that are connected in some way. For example, here we've got 1, 2, 3, 4 and 5 vertices or nodes, and they are connected in this case by 1, 2, 3, 4, 5 edges or arcs. So a graph is simply a set of vertices connected by some edges. Well, what's a network then? Well, network is a type of graph. The only difference is that the arcs, the connections, have certain weights assigned to them. So for example, the same graph as we had before, very similar, but this time I'm saying to connect that node to that node costs you £35, that node to that node costs you 25, for example. Now these weights could be anything. They could be costs, like costs of for example, cables, or it could be distances travelled, etc. So all a network is a weighted graph. Okay, well, what's a spanning tree then? Well, a spanning tree is a tree, and a tree is a connected graph with no cycles that connects every node in the graph. So to show you what I mean, let's start off with a very simple graph with one node. How do I connect that to itself? Well, it is itself, so it doesn't require any connection. So a connection without creating any cycle would have 0 arcs in it. It would just be as it is. However, what if I had two nodes? How could I connect that without creating a cycle? Well, I could all I could do is connect it like that with one arc. Now do remember, I can connect these things in any ways. I could connect it like that, but I would have a cycle there because I could go from here to here and back again. I don't want that. So all I want is things without cycles in them. So for two nodes I require one arc. What about three nodes? How could I connect them? 1, 2, 3. So that they are connected, I can find a path between any one of them, but there is no cycle. For example, that is no good to me because although they are connected, there is a cycle there. I don't want that for a spanning tree. So one way I could do it is I could simply connect that one and that one, or I could connect that one and that one, or I could connect that one and that one. So with three nodes I'm going to require 2 arcs, and so it continues. I think you can see the pattern here. I always require one less arc than there are number of nodes. So the general rule for creating a minimal spanning tree with n nodes, if I want a spanning tree of n nodes, I'm always going to have one less number of arcs, i.e. n minus 1 arcs. So a spanning tree of 11 nodes will have 10 arcs, for example. Okay, the aim of this lecture is to, actually just before I do that, just pause for a moment, maybe pause the video. Here's a graph. It's got 1, 2, 3, 4, 5 nodes, and currently it's got 1, 2, 3, 4, 5, 6, 7, 8 edges. Just wondered if you could pause the video for a moment and see if you could find 3 spanning trees for those 5 particular nodes. Now remember, 5 nodes, you're going to require 4 arcs. Pause the video, have a few minutes, just see if you understand what a spanning tree is by creating 3 for the graph above. Okay, you can unpause the video. Just going to show you an example of 3. Here's an example of one of them. One could look like that. Everything's connected there, but there are only 4 arcs. and no cycles. Similarly, everything connected without cycles. Similarly, everything connected without cycles. So that's what a spanning tree is. It's a way of connecting all the nodes, making sure you can always find a path between any two nodes, but there are no cycles within those connections. Okay, at last we move on to what the point of today is. And the point of today is to find a spanning tree of any particular network such that that spanning tree is minimal, has the smallest possible weight. Remember what we're trying to do. We are trying to connect up all the nodes in the network so that between any node you can find a path, and that particular spanning tree has no cycles and is smallest in weight. Okay, let's have a look at this particular one here. Let's consider what we've got. We've got ourselves a network. For example, the nodes are A, B, C, D and E. So we've got ourselves 5 nodes or vertices, and currently there are a lot of arcs there. For example, the arc AD has a weight 8, the arc BD has another weight 8, the arc AE has a weight 2. We're trying to find a spanning tree so that all those nodes are connected, but it's minimum in weight. So we know from our previous work that we're going to require 4 arcs, always one less than the number of nodes. So we could go about by trying to create spanning trees and then list them all and see which one's smallest. So let's have a go at that. Here's one for you. 4 arcs, weight 26. Here's one for you. 4 arcs, everything connected, weight 22. Here's another one for you. 4 arcs, everything connected, weight 24. So I could go on by listing all of these and find which one's the smallest. So currently, my best guess is 22 out of the ones I've done so far. It's not a very efficient procedure to just list out spanning trees. As you could imagine, as the nodes increase, the number of variations of spanning trees will go up dramatically. We need an algorithm. Hence, Prim's algorithm will help us. Prim's algorithm, or sometimes called the greedy algorithm, finds a minimal spanning tree for us in a nice, easy 3-step procedure. Looking back at the same network we were dealing with before, let's apply Prim. Prim says that to find the minimum spanning tree denoted capital T, we select any node of the network to be the first of T. So why don't we pick A in particular? That's going to be our first node. And we've done step 1. Step 2 says, consider which arcs connect nodes in T to nodes outside T. What arcs connect nodes in T to those outside? Well, the only arcs connected to T, which is currently just node A, are the 2, the 8, the 4 and the 6. It says pick one with the minimum weight, and if there are more than one, choose any. Add this arc and node to your minimal spanning tree T. What's smallest out of 2, 8, 4 and 6? Well, 2 is, so I'm going to include this 2, and I'm going to include the node E now, and I'm also going to include the arc AE. So far that's what our minimal spanning tree looks like, and we've done the first round of step 2. What does step 3 say? It says repeat step 2 until T contains every node of the graph. I've currently only got 2 nodes in my spanning tree. There are another 3 left out. I'm going to have to keep going with this at least 3 times now. Okay, which arcs connect nodes in T to those outside? The 6 connects outside, the 4 connects outside, the 8 connects outside, but also we've got a new node E to consider. The 7 will connect outside, this 4 will connect outside, and this 6 will connect outside. What's the smallest out of 7, 4, 8, 6, 4 and 6? Well, 4 is. And Prim tells us in step 2 that if there are two the same, choose any. So I'm going to pick this 4 here to be the one I go for. And I'm going to connect in this node here, C, via that path of 4. And I'm also going to say AC is now in my minimum spanning tree. Okay, I've got 3 nodes now. I've got 2 more to connect up. Let's go back to step 2. What now? What arcs connect to outside of our current spanning tree T? Well, now we've got to have the 5 in there because 5 connects to B and B is outside. We've also got to have this 9. Going back to A, we've got the 4 already. This 8 is good and the 6 is good. Going to E, this 6 is good here. This 4, however, is no good. It connects to something already in our spanning tree, so we can never take this 4 anymore. Even in more particular, if I was to create an arc EC, I would then have a cycle, and we know a spanning tree cannot have any cycles in. ED is still a good one. So what's the smallest out of 7, 9, 6, 8, 6 and 5? Well, 5 is, so I'm going to include this 5 here. I'm going to include the node B, and I'm going to include the arc CB. We're nearly there now. All we've got to do is connect in D. Well, let's just think what can connect us there. AB is no longer one that we can choose because it would create a cycle, or it would bring us from T back to T. EB is no longer any good. What else have we got? ED is good now, AD is good now, and BD is good now, and CD is good. What's the smallest out of 7, 9, 8 and 8? Well, 7 is. So I'm going to take that 7. I'm going to include node D, and finally I'm going to include the arc ED. And hence I've created myself a spanning tree here. It's got 1, 2, 3, 4 edges. Everything's connected up, and it has weight 7 plus 2 plus 4 and plus 5. So I give that a total weight of 18. So Prim has found for us a spanning tree that is of weight 18, and it turns out Prim always finds for us the minimal spanning tree. Hence we found it's 18. Let's just check back to our others. We had 24, 22, 26. Prim has beaten that for us with 18. Okay, just finally wanted to show you how to work out Prim's algorithm in matrix form. Sometimes when the number of nodes is quite big, this is an easier way to do it. First thing we do is we convert our network into a matrix format. Well, we have nodes A, B, C, D and E, and they're connected to the nodes A, B, C, D and E. Now clearly A can't connect to A, B can't to B, C can't to C, D can't to E, and E can't to E. So those we ignore. But what weight connects A to B? Well, A to B is connected with 6. And A to C is connected with 4, A to D is connected with 8, and A to E is connected with 2. Now in this particular graph it's symmetrical. This isn't a digraph, a directed graph. AE is the same as EA. So I can say that going downwards here, the symmetry here, the connection B to A is the same as A to B. So it's 6, C to A is 4, D to A is 8, and E to A is 2. So I can just from now on just copy downwards. Not always the case, but in this particular graph there's no direction assigned here. AB is the same as BA. So what's BC? BC is 5 here, BD is 8, and BE is 6, 5, 8, 6, 5, 8, 6. Let's go from C. C to D is 9. C to E is 4. 9, 4, 9, 4. And finally D to E is 7. So that 7 goes there, that 7 goes there. So we've converted our network into a simple matrix form. Okay, now what do we do? Well, Prim's via a matrix form says select any node to be the first of T. Let's select A. Step 2 says circle the new node in T in the top row, which I've just done, and cross out the row corresponding to this new node. I've circled A, so I'm going to cross out row A, like that. Step 3, find the smallest weight left in the columns of the nodes of T. Currently, A is the only thing in T, so I'm going to find the smallest one, and it's 2. So AE is in my minimal spanning tree here. So AE is the first one I've got. Okay, then it says that will join. Now it says repeat steps 2 and steps 3. Circle the new node of T in the top row. The new node is E. And it says cross out the row that corresponds to this. So cross out now the rest of row E, apart from the one you've circled. And then it says find the smallest weight in the columns of the nodes of T. A and E are currently in T. So 6, 4 and 8, 6, 4 and 7. So I'm going to pick the smallest one of these. Now there are 2 4s, I can choose any, so I'm going to say choose that 4 there. Therefore that includes EC of 4 into my minimal spanning tree. Repeating step 2, circle the new node of T in the top row, so circle C and cross out the Cth row. So I'm going to cross all this out now. Step 3, find the smallest weight left in the columns of T. I've got 6, 8, 5, 9, 6 and 7. The smallest weight is a 5 here, and it's in the Bth row. So I'm going to include CB now into my spanning tree. So CB is now in my spanning tree, highlight B and cross out the Bth row. Now I look, I find the smallest weight left in the columns. There's an 8 here, an 8 here, a 9 here and a 7 here. The smallest is clearly that 7. So ED is also going to be included in my minimal spanning tree. ED there. I'm going to circle D up here and cross out the Dth row. So this format has produced for us. Now we can stop because we have every node circled at the top, and my minimal spanning tree is 2 plus 7 plus 4 plus 5, which again you'll find is 18 and gives me a minimum spanning tree. Thank you for listening. I hope you found this video tutorial useful in using Prim's algorithm to find minimum spanning trees. Thank you. As a final exercise, I thought I'd set you a few questions on Prim's using the graphical method and Prim's using the table or matrix method. Pause the video now, have a go at questions 1A and B to find the minimum spanning tree starting from vertex A using Prim's. Pause now. And the answers are as follows. So there are your minimum spanning trees with your total lengths. And last 2 questions using Prim's via the matrix method. Please find the minimum spanning trees using Prim's algorithm, again starting from vertex A. Pause the video now. Okay, and the solutions to those 2 questions are as follows. And hence you should now have done 4 questions where you've checked whether you can use Prim's algorithm to solve for a minimal spanning tree using a graph method and a table method. Thank you.